My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about X-rays, how to produce X-rays, the structure of the device used to generate X-rays. Also, we'll learn about the two types of X-rays, uses and properties of X-rays. So please stay with us. Atomic spectra and X-rays. First of all, let's discuss types of spectra. As a matter of fact, we've got two types here, invisible spectra, and this invisible spectra, yes, consists of infrared and ultraviolet light. This was about the invisible one. And we've got, yes, visible spectra, which divides into emission spectra, and emission spectra, and absorption spectra. So visible spectra contains emission and absorption spectra. And what about emission spectra? It consists of two types also, continuous and bright line spectrum. Okay, so let me say it again, talking about the different types of spectra. We've got visible and invisible. And what about the visible? We are so much concerned with visible spectra. It consists of two spectra, emission and absorption. Emission consists of continuous spectrum and line spectrum. And also absorption spectrum is called dark line spectra. So let's take it one by one. Starting with emission spectra. Yes, what about it? Emission spectra are produced when electrons fall from higher energy levels to lower energy levels. So, yes, this type of spectra is produced when electrons fall from higher energy level to lower energy level. And it consists of, it includes two types, continuous spectrum. What about continuous spectrum? We want to give it a definition. It is the spectrum which contains wide range of frequencies. It is the spectrum which contains wide range of wavelengths or frequencies. In a continuous spectrum, there is something special that characterizes this kind of spectrum. In a continuous spectrum, the colors gradually change from one color to the next. Examples for continuous spectrum. The spectrum given out by a glowing hot solid object, such as incandescent filament, the incandescent filament of the lamp. The spectrum given out by a glowing solid, okay, for example, incandescent filament of a lamp, or the spectrum given out by a glowing molten solid. Glowing molten solid is then a liquid. So spectrum or the light given by, yes, molten liquid. And now talking about the second type of the emission spectrum, which is bright line spectrum. And this is very important spectrum. It is the fingerprint of elements. It is definition of bright line spectrum. It is the spectrum which consists of a number of colored, narrow, bright lines with wavelengths characteristic of the element which emits light against a dark background. Okay, bright line spectrum is given out by a glowing gas. If you remember, continuous spectrum is produced by a solid, glowing solid. But bright line spectrum is given out by a glowing gas. Your attention please, we've got something here to mention. Each gas has its own bright line spectrum. Each gas has its own bright line spectrum. That's why we call bright line spectrum the fingerprints of elements. Flame tests for certain solids are examples of bright line spectrum. As in a flame test, the solid material is no more a solid. The solid material vaporizes. Bright line spectra are the fingerprints of atoms. Let me focus on this. Bright line spectra are the fingerprints of atoms. And now it's high time to talk about the last spectrum, dark line spectrum or absorption spectrum. Definition of this spectrum, it is the spectrum which consists of dark lines. It consists of dark lines, not colored lines. So it is exactly the opposite of the bright line. Once again, it is the spectrum which consists of dark lines indicating the absence of certain wavelengths of light against bright colored background of continuous spectrum. Against bright colored background of, yes, continuous spectrum. Absorption spectrum is produced when a gas or vaporized element is exposed to a continuous spectrum, exposed to white light. Okay, let me say this piece of information again. Absorption spectrum is produced when a gas or vaporized element is exposed to a continuous spectrum, is exposed to white light. Example for absorption spectrum: Fraunhofer dark lines which appear in the solar spectrum. This is very important thing here, important piece of information. Fraunhofer dark lines are example for absorption spectrum. They appear in the solar spectrum. We've got here a question. You may be encountered with a question like, give reason for. Hundreds of dark lines appear in the sun's, yes, spectrum. Hundreds of dark lines appear in the sun's continuous spectrum. Okay, they appear due to the presence of certain elements in the atmosphere of the sun. These elements are in vaporized form, and each one of them absorbs its own characteristic wavelengths. Accordingly, dark lines appear. Once again, these elements found in the atmosphere of the sun are in a vaporized form, and each element absorbs its own characteristic wavelengths, so they, yes, disappear from the spectrum, and we've got dark lines. And now talking about X-rays. As a matter of fact, X-rays are invisible electromagnetic waves. But there is something very important that characterizes X-rays. They are invisible electromagnetic waves of short, yes, wavelengths. Wavelengths range from 10 to the power of negative 13 meter to 10 to the power of negative 8 meter. They lie in the region between gamma rays and ultraviolet. X-rays lie in the region between gamma rays and ultraviolet. And now, talking about the device used, yes, for generating X-rays, it is college tube. So what about college tube? It is the device used for what? Yes, for generating, for producing X-rays. Structure of the device is shown in front of you, and we'll talk about each component of the device. So, the diagram shows a modern X-ray tube called college tube. This type of tube was devised by college in 1913 in the, what about the structure? In the tube we've got something here. We've got a filament. Function of the filament when heated is to produce, yes, electrons. Okay, in the tube, electrons are given off from the cathode by thermionic emission. Electrons are given out from the cathode, as I said, by thermionic emission. These electrons are accelerated by a very high potential difference produced between the cathode and anode. And electrons which are accelerated, having very high kinetic energy, will collide with a target made of tungsten, okay, or molybdenum target. This target is embedded in a copper anode. So we've got a cathode, and function of the cathode is to produce electrons, and we've got copper anode, and between these two electrodes very high accelerating voltage is applied. So we expect the electrons emitted from the cathode to have very high kinetic energy. Then we'll try to stop it, okay, and you'll observe something very important. When we try to stop these electrons, okay, they lose their energy in form of photons having very high frequency, so they lie in X-rays region. Okay. Once again, we've got something here. The anode gets very hot, and it's therefore made of solid copper. Solid copper is a good conductor of heat, and we've got, and this anode, okay, is fitted with the cooling fins. That's to say the anode has to be cooled to prevent its damage. And now talking about X-ray spectra. First of all, the X-ray spectrum consists of two parts. The first is a continuous spectrum. It contains, the continuous spectrum contains every wavelength within a certain range. Every wavelength within a certain range. And how this sort of this spectrum is produced? This spectrum is produced due to the radiation emitted as the colliding electrons, thermionic electrons, are decelerated or slowed down by the retarding fields produced by the electrons of the target's material and by collisions. Hence, an electromagnetic radiation is released according to Maxwell-Hertz theory. This radiation is continuous and is called the soft spectrum or the breaking spectrum of X-rays. The breaking effect of the surrounding electrons gives rise to electromagnetic radiations which covers a wide range of wavelengths. Second type of X-ray spectrum is the line spectrum, but it is produced due to something totally different. Your attention, please. The peaks, spikes on the spectrum actually are the line spectrum of X-rays, and they are, yes, characteristic to the material of the target. The peaks, the spikes on the spectrum are characteristic of the material of the target. The line spectrum is produced when electrons from the inner energy levels are removed. So we've got, yes, vacancies here. Electrons from the innermost energy levels are removed completely by the bombarding electrons. An electron, so the next step, an electron from an outer energy level relaxes, falls to fill the vacancy, the hole, emitting a photon of a definite wavelength. That's why it is characteristic to the material of the target. The electron, okay, we've got electron that falls from higher energy level to fill the hole, the vacancy. And when this happens, yes, a discrete amount of energy is released in form of a photon having a definite wavelength, which has something to do with the structure of the material of the target. So it is characteristic to the material of the target. Talking about the wavelength of this emitted photon, yes, delta E is the difference between the two energy levels, and it is equal to h nu. So h nu is the energy of the released photon. Nu is replaced by c over lambda, so the photon have an energy which is equal to h c over lambda. And of course you can calculate the wavelength from this expression. Okay, thus giving sharp line on the spectrum. We've got important notes here. The intensity of the X-ray beam depends on the number of electrons striking the target per second. Let me say it again. The intensity of the X-ray beam depends on the number of the electrons striking the target per second. And this is controlled by the cathode heater current, the current that flows through the filament. The penetrating power penetration power, okay, hardness of the X-rays depends on the accelerating voltage. Okay. The process, here we've got something interesting. The process in which X-ray is produced is the reverse of the photoelectric effect. But how? Let me say it. In photoelectricity, in photoelectric effect, a photon ejects an electron from a metal target. But, okay, when we produce X-rays, the reverse occurs. Exactly the opposite occurs. Here in this process, when X-ray is produced, an electron produces a photon, yes, by striking a metal target. And now talking about applications of X-rays. Talking about applications of X-rays. As a matter of fact, X-rays are used in studying the structure of some materials. The question is why? Simply because the spaces between the atoms and crystals are ideal for X-ray diffraction. So interference patterns are produced, and these patterns are reveal the structure of the crystal. Okay, so once again, why X-rays are used to study the structure of some materials? Because the spaces between atoms are ideal for X-ray diffraction. So when X-ray diffraction occurs, what happens next? We've got interference patterns, and these patterns reveal the structure of the crystal. X-rays are used to check defects in metallic structure. They are used to check defects in metallic structures in metal casting, because X-rays have high penetrating powers. Also, X-rays are used in detecting fractures and cavities in bones. So, they are used in detecting fractures and cavities in bones, a broken bone or a tooth cavity. And now talking about properties of X-rays. First of all, they are photons, okay? So they are not charged, okay? So they are not deflected by electric and magnetic fields. They are highly penetrating and can pass through many solids which are opaque to ordinary light, such as wood and flesh. Let me say it again. They are highly penetrating and can pass through many solids like wood and flesh. They cause fluorescence. They cause photoelectric effect and Compton effect. They ionize gases. Also, they are propagated in straight lines with the velocity of light, which is equal to 3 times 10 to the power of 8 meters per second in space. As a matter of fact, X-rays, since they are electromagnetic waves, yes, X-rays consist of electromagnetic waves of very short wavelength that show reflection, diffraction, and interference. And this shows the wave nature of X-rays. And now let's answer some questions together. Give reason. X-rays have valuable engineering uses. Yes, X-rays may be used to check defects in metal casting and crystal analysis. So X-rays may be used to check defects in metal casting and crystal analysis. X-rays are used in studying the structure of some materials, in analyzing the structure of crystals, because the spaces between the atoms in crystals are ideal for X-ray diffraction. So interference patterns are produced, revealing the structure of the crystal. Another give reason. X-rays have valuable medical uses. They have valuable medical uses because X-rays are used in two main areas. Diagnostic areas, in the detection of a broken bone or a tooth cavity. Therapeutic areas, and in the treatment of malignant cancers. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.